Okay, so now we're on the last piece of chi-square test for independence or homogeneity, and we want to be able to distinguish between a chi-square test for independence and one for homogeneity. So I'm going to give you a couple keys for distinguishing which of the two tests to use. You have to consider how the data were produced. So if the data comes from a single random sample with the individuals classified according to two categorical variables, you use a chi-square test for independence. If the data come from two or more independent random samples or treatment groups in a randomized experiment, you want to use a chi-square test for homogeneity. Another way to think about this to help you distinguish the two tests is to consider the two sets of totals in the two-way table. In tests for homogeneity, one set of the totals is known by the researchers before the data are collected. However, in a test for independence, neither set of totals is known in advance. Let's look at a couple examples and then run through a full test to solidify this in our brains. So problem A here, we have two researchers asked 150 volunteers to recall the details of a car accident on video. 50 of the volunteers were randomly assigned to respond to the question about how fast were the cars going when they smashed into each other. Another 50 volunteers were randomly selected or randomly assigned, excuse me, the same question, but with words smashed into replaced by the word hit. Researchers did not ask the remaining 50 volunteers, which was the control group, to estimate the speed at all. A week later, researchers asked all 150 volunteers if they saw any broken glass at the accident, and there wasn't any. The two-way table summarized each group's response to the broken glass question, which chi-square test should be used to analyze this data. So here, because this was an experiment with randomly assigned treatments, a chi-square test for homogeneity should be used to analyze these results. Remember, the researchers determined in advance that there would be 50 volunteers in each group. So the groups were known, the group size were known before the experiment took place. So only one set of totals was free to vary. That would be whether they said yes or no within each of the groups of 50. This indicates a test of homogeneity is the correct choice. Now, problem B here, to become a naturalized U.S. citizen, a person must take a civics test consisting of 10 questions randomly selected from a list of 100 predetermined questions. A score of 6 or more is a passing score. Three researchers wondered if the ninth and 10th grade students at their school were just as likely to pass the test as 11th and 12th grade students. They randomly selected 58 students from their school of 1,853 students and gave them the test. The two-way table summarizes the results. So here we go. Which chi-square test should be used to analyze the data? Well, here we go. The data came from a single random sample, n equals 58, from the high school, with individuals classified according to two categorical variables, grade level and result. So a chi-square test for independence should be used to analyze this data. Also, if you think about how they conducted the single random sample, they didn't know in advance how many would be ninth and 10th graders or 11th and 12th graders. Also, they didn't know if they would pass or fail the test. So both sets of totals were kind of free to vary before they conducted, before they got the information. So this indicates that a test for independence is the correct choice. So if we go back to problem A again, here we have the table from problem A, and this was the car accident. Um, how fast were the cars going when they smashed into each other? Okay, we want to state the hypothesis for that part. So the true proportion of people like the ones in the study who would say there was broken glass are the same for all three treatments, and the alternative would be not the same. You wouldn't say it's different for all three treatments because that would imply that all three proportions have to be different. And remember, um, we're looking for at least one to be different than expected. Okay, so the p-value for an appropriate test is 0.02. What conclusion would you make at the 0.01 significance level? So, because a p-value is of 0.2 is greater than our significance level, we would fail to reject the null, and there would not be convincing evidence that the proportions of people like the ones in the study who would say there was broken glass are not the same for all three treatments. Now, what if the significance level was 0.05? Now, just a word here. You can't just change the significance level at the end if you don't get the result you were looking for. You have to state the significance level before you carry out the test. We're just saying, what would happen in this case. And at 0.05, we would reject the null in that case because our p-value of 0.02 is less than 0.05. There is convincing evidence that the proportion, blah, 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 is not the same for all three treatments there. So, name two ways we could increase the power of the test. So, the first thing to increase the power of the test, you could make the significance level greater than 0.02 or make the group size greater than 50. The other way, well, that is the second way that we have it there. You make the significance level greater than 0.02 or you make the group sizes larger. All right, guys, that's it for this one. Hope that was helpful to you. Reach out if you have any questions. Take care.